In 1960, near Lamarco, Chile, something earth-shattering happened. Or maybe that should be earth-waving. The biggest earthquake ever recorded hit, measuring a 9.5 on the Richter scale. There were somewhere between 2,000 and 6,000 casualties, mostly within the local area. But did you know that the waves from that earthquake could be felt almost at the opposite side of the Earth? Some of those waves are able to reverberate and refract through the mantle and even the core of the Earth. But why is it that the aftershock of an earthquake so often causes more damage than the original earthquake itself? And how do the longitudinal waves in this random song hit your ear, make you want to cover them up? Personally, I recommend earplugs. Earthquakes, water waves, light and sound, all will be revealed. Let's talk about waves. Welcome to Flip Physics. Today I'm going to talk about waves. What exactly are waves? Is this a wave? No, waves go like this, right? Or maybe like this. Well, not really, but a Mexican wave does have some features in common with a real wave. There is a periodic movement, and it does at least look like energy is moving through the wave. A wave is a periodic vibration in space and time that carries energy. Here's an example of a wave. It's continuous and periodic. It repeats the same pattern, carrying energy with it as it goes. But how do we know waves carry energy? Well, a lot of ways. But really you only have to take one look at a beach. This sand has been broken down by wave after wave, by the power of the sea over years and years and years. Rock has been turned into these fine granules of sand. That takes some serious energy. I certainly couldn't take this rock and turn it into this. I don't have the energy to do that, but within the power of the sea, within those waves, is the energy to do that. If we eat animals, those animals ultimately got their energy from plants, and those plants got their energy from the sun through photosynthesis, from the light waves that the sun sent towards the earth. So just from the way we eat, we can see that the sun provides energy, and that light waves therefore carry energy. Okay, so let's go through a few important features of waves that you should know about. Waves have peaks or crests. They also have troughs. They have an amplitude measured in meters and a wavelength measured in meters. The wavelength can be measured either peak to peak or trough to trough, or the bit that goes up to the next bit that goes up. As long as you start the same part of the wave as where you finish, that will be one wavelength. But this graph is y versus x. It's basically like looking at a water wave side on and taking a picture of it. It shows you just one instant in time in the y direction and the x direction. It tells you what that wave looked like at that instant in time. Instead of showing a wave by doing a y versus x graph, we could instead plot the y direction or x direction against time. How much displacement the wave has in a particular direction over time. Waves make particles move up and down, and so over a period of time they'll move up and down in a certain pattern. That pattern looks the same as the previous graph, but here this distance is the time period of the wave, the time it took for one full wave to pass. The wavelength is literally if you took a ruler and measured how long the wave is, but the time period is how long it takes for one wave to pass. Or in other words, you could say that the time period is the number of seconds per wave. If you take the inverse of that, the reciprocal of it, you get the opposite. Instead of seconds per wave, you get the number of waves per second. That's called the frequency, measured in hertz. The computer screen that you're looking at right now most likely is refreshing its picture at a rate of 60 hertz. That means that the picture refreshes 60 times every second. And if you're looking at water waves and a full wave passes you 5 times in a second, the frequency of that wave is 5 hertz. Last of all, the wave speed is defined as the number of meters of wave that pass every second, meters per second. It's the wavelength divided by the time period, which is the same as the wavelength multiplied by the frequency. Sometimes you'll just know v, you'll know the speed of the wave. For example, the speed of sound is 340 meters per second on average, and the speed of light is 3 times 10 to the 8 meters per second. So sometimes you'll have a number to plug into this equation just by knowing what type of wave it is. Speaking of types of waves, there are 3 main ways that we can categorize waves. Transverse versus longitudinal, having a medium versus having no medium, and traveling versus standing waves. Transverse waves are what most people think of when they think of waves. The particles are vibrating at 90 degrees to the direction that the wave is moving. If we grab this slinky and go like this, we have a transverse wave, because we're vibrating the wave at 90 degrees to the direction it's moving. This wave is moving this way, but it's vibrating at 90 degrees to that. Ocean waves also work this way. Electromagnetic waves such as light or radio waves or infrared, and the secondary wave of an earthquake, otherwise known as the aftershock, is also a transverse wave. Longitudinal waves still have an oscillating pattern, but it's a pattern of density. High density and low density, a peak and a trough. High density areas, the peaks, are called compressions. And low density areas, the troughs, are called rarefactions. And because of the way these waves work with particles hitting each other as they go along, making these compressions and rarefactions, a longitudinal wave is where the vibrations are in the same direction, the same plane as the wave is moving. With a slinky, we can make a longitudinal wave like this by sending pulses down the slinky. The vibration is this way, and the wave is also moving this way. The vibration and the direction of motion are parallel to each other. That's the definition of a longitudinal wave. The classic example of a longitudinal wave is sound. This guitar string vibrates, causing particles to hit each other. Those particles hit air molecules that hit each other, and the vibration continues through the air until it reaches your ear, at which point it hits the eardrum in your ear, causing your eardrum to vibrate. It's just a series of collisions of particles, of vibrations passing through the air. And the first part, the initial hit of the earthquake, is also a longitudinal wave. And in case you're wondering why we even call these vibrations waves, if you plot the density of those air molecules, if you plot the compressions and rarefactions, you'll find the density oscillates up and down in this same characteristic sinusoidal wave pattern. Now, let's go back to earthquakes. Why is it that the aftershock causes more damage? Well, let's do a little experiment. Let's say that this envelope represents the ground, and these little candles represent buildings. Although obviously actual buildings would be much better supported, much better connected to the ground. But the question is, what's more likely to make these buildings fall over? If I go like this, or either sideways or up and down, or instead if I start waving the ground like this. Human buildings can take a little bit of a beating if you start moving the ground in linear fashions, but as soon as the ground starts to wave, that tends to be bad. So since the aftershock is a transverse wave, it's the aftershock that tends to cause the most damage. The ground going like this is very difficult to plan for. I mean, you don't really expect your ground to start rippling like the ocean. I mean, unless you're from California. But I'm from England. Like, our ground stays where it is. The second way to categorize waves is medium versus no medium. Most waves need a medium. They need a material to move through. Sound is an example of a wave that works that way. In space, no one can hear you scream. See, you can't hear it. But if you've taken out the air, you really can't hear anything at all. Electromagnetic waves, however, like light for example, they don't need a medium. That's because an electromagnetic wave contains vibrations in the electric and magnetic fields. And as we know from studying electrostatics and magnetism, those forces can act in a vacuum. And of course, if they didn't work in a vacuum, then we wouldn't get any energy from the sun. All those light waves from the sun would not get to us. And that would make the Earth a very boring, dull place indeed. So all of these things are electromagnetic waves. All of these things don't require a medium. The radio waves that make your car radio work and also allow you to talk on your cell phone, the microwaves that cook your food, the infrared that makes human bodies feel hot, the visible light that makes your eyes work, and the gamma rays produced in nuclear reactors. All of these are electromagnetic waves. They are waves that don't require a medium. And last of all, the final way to categorize waves is to distinguish between traveling waves and standing waves. Traveling waves are like water waves or slinky waves. They travel in a specific direction. But if you have two of those traveling waves going in the opposite direction to each other, they can interfere, creating something called a standing wave. You could do that by having two separate waves going in opposite directions, or continually sending one wave, allowing it to bounce off the end, so that the first few waves interfere with the later waves. Either way, if you have two waves going in opposite directions, you tend to get standing waves. A standing wave looks like this. It's just a series of sinusoidal wave shapes bouncing up and down periodically. The parts that don't move are called nodes, and the parts that move the most are called antinodes. Take a closer look at this graphic to see how they work. Whenever two peaks in the original two waves are overlapped with each other, you get a bigger peak in the standing wave. Whenever two troughs overlap with each other, you get a bigger trough in a standing wave. And when a peak and a trough are over the top of each other, you get no wave in the center. You get a node. Standing waves can have long, complicated equations associated with them, like this one for example. But the principles are pretty simple. They're really just the principles of interference of waves. If you have two peaks, you get a bigger peak. If you have two troughs, you get a bigger trough. If you have a trough and a peak, they cancel out to zero. It's just the way that two overlapping waves interfere with each other. Before this video comes to a close, I'd like you to look at this clip and tell me if you think it's real or fake. Well, it's kind of both, but I would say overall it's mostly fake. It is a real video that was taken just as it appeared to be taken, but it's actually just a weird effect that happens due to the iPhone's rolling shutter. But thank goodness that waves on strings aren't that complicated, because if they were, we wouldn't have the beautiful harmonious music that humans have enjoyed for millennia. Each string vibrates most strongly at a single particular frequency. It's called the natural or fundamental frequency of a string. When you pluck a guitar string, or blow a horn, or run a bow across a violin, you create a standing wave at that frequency. And that standing wave vibrates to give you the notes that you wanted. The same thing happens when you sing to the air inside your vocal cords. So we should be very thankful for waves and the way they work, so that this D is always a D. Thanks for watching Flip Physics. If you like this video, you can press the like button. You can also subscribe or go to the flipphysics.net website. But most of all, don't forget to leave a comment below with your questions, thoughts and suggestions. Until next time, keep questioning.